continue topic of absolute and conditional convergence. So 18.1, let me call it absolute and conditional convergence of series. Examples: rearrangements, products. So I'll start with a couple of examples, typical for absolute and conditional convergence of series. Investigate. I'll write shortly. I'll omit absolute and conditional convergence. Just we'll look at the series sine nx power n power alpha, and for simplicity we'll consider maybe for, let's do it for arbitrary alpha, real, why not? So and few general words. In fact, investigation of convergence of series is quite analogous to examples when you are asked to study convergence of improper integrals. So they are twins, in fact. Imagine you have an integral and you have a similar thing. By the way, it explains why I didn't touch the possibility to use integration by parts for improper integrals. Because for series it is not so easy. Okay, you may consider Abel transform as an analog of integration by parts, but it is not so fast. Okay, so we have a series with two parameters, alpha and x. In fact, a little bit later we'll consider it as an example of functional series, but for a moment we are talking about usual series with two parameters, x and alpha. So also x is real. And the simplest thing is to prove absolute convergence for certain values of alpha, namely, so first part. Let's estimate general term of our series. As we know, the values of trigonometric function sine are always less or equal than 1. So we have 1 over n power alpha. And also we know that the series converges if and only if alpha is greater than 1. Those two facts together imply by comparison test that the series of modulus converges for alpha greater than 1 and x in R arbitrary. Hence, we deduce that the series, the original series, absolutely converges for alpha greater than 1 and x in R. And by the way, please be careful. Look, here it is written if and only if, right? So we know this series converges if and only if alpha is greater than 1. It allows to deduce only those assertions, nothing else. What I mean? Look, you can suggest, okay, if alpha is less or equal than 1, then what it means? It means this series diverges, right? And what it says about our series? The answer is nothing. Why? Because how comparison test works? If we have such an inequality, right, then convergence of this series implies convergence of the series to the left, right? But divergence of this series doesn't imply anything. Because, you know, convergence of greater series implies convergence of smaller. Divergence of smaller implies divergence of greater. But divergence of greater doesn't imply anything. So, if alpha is less or equal than 1, then, as you see, nothing is deduced, right? So, this works only for alpha greater than 1, it gives absolute convergence. Okay? Okay, second part. So it was the easiest part. Now we want to understand how we can prove convergence of our series without comparison test. It means we cannot estimate. Then what we can apply? We can apply Dirichlet test. So, apply Dirichlet test. What it says? It has two halves, two suppositions to be checked, in fact, right? So, first of all, we have to check two suppositions. One is about boundedness of partial sums. Which partial sums are bounded? Or at least we may hope on boundedness of this partial sum. So, we want to discuss partial sums of this kind. We want to prove that they are bounded. How? The idea is as follows. So we multiply by sine x over 2 and divide by sine x over 2. Then what happens? Product of two sines is equal to difference of two cosines, right? So cosine of difference, k minus 1/2 x, minus cosine of the sum over 2 sine x over 2. Now, that is a telescoping sum, right? And what remains? Okay, k equals to 1 gives cosine x over 2 minus the last gives cosine and plus 1/2 x and 2 sine x over 2. Now we can estimate less or equal 1 over sine x over 2, right? It gives a bound for arbitrary partial sum. So, of course, it is valid when x is not equal to what? 2 pi n, right? An integer. We should exclude it, right? Otherwise, we have a 0 in denominator. But what happens when x equals 2 pi n? Substitute from the beginning. If x is integer multiple of 2 pi, then sine equals to 0, right? So we have identically 0 terms, and the series converges, of course, right? We don't need to study anything, right? And we have absolute convergence for arbitrary alpha, right? If the series consists only of zeros. But that is very exclusion. I mean, when x equals to 2 pi n. And for x not equal to 2 pi n, we have first condition of Dirichlet test is satisfied, right? Now, what's about second condition? Second condition is that the sequence is monotone and limit is equal to 0. That is what we need to apply Dirichlet test. When it's true, for which values of alpha? Monotone is always, right? And that one? Alpha should be positive, right? Positive. Alpha should be positive. So what it gives altogether by Dirichlet test, our series converges for alpha greater 0, x real, right? Okay, but next question, how it converges? Either absolutely or conditionally. That is a question, right? In fact, you see, if alpha is greater than 1, then we are not interested, in fact, right? We know it converges because it is absolutely convergent. Hence, it is convergent, right? So, for alpha greater than 1, in fact, there was no sense even, right, to apply. It's overcrowded proof for alpha greater than 1. Okay, then what to do? So the question how? How, right? How for alpha between 0 and 1? That is the question, right? And of course, x not equals to 2 pi m integer, right? That is still a question which we need to answer to complete the second step. Okay, so it means we need to check absolute convergence. So I prefer to stay on the same step, although you may start new one, doesn't matter. So the question is absolute convergence of this series alpha from 0 to 1, x not equals 2 pi m. Because if x equals, then we have zeros, it means we have absolute convergence, and if alpha is greater than 1, then we have absolute convergence by the first step. So that is the question, right? So we need to study the series of modulus. And here, the typical idea is as follows. Look. Of course, remember we are with the same supposition, right? So, the number sin nx is a number between 0 and 1. If we take square of this number, it will be less or equal, right? If you have a number which is less or equal than 1 and you take it square, then you diminish it, right? In general. So I can put here sine squared nx. Now we have trigonometric formulas, right? Double argument. So that is 1 minus cosine 2nx over 2n alpha, right? Now, this series sine squared nx over n power alpha diverges for values of alpha x under question. Why? Why? Since the series diverges, alpha is, look, 1 over n power alpha converges if and only if alpha greater than 1, right? So if alpha less or equal than 1, then it diverges. And the series of cosine 2nx over 2n power alpha converges for the same values of alpha. by Dirichlet test. Again. Of course, you can ask why the last. What you should to do? You have to repeat. Instead of sine, you have cosine. Also, you multiply by sine x, not by sine x over 2. And similar consideration. Similar consideration works for this series as well, right? And look, so now you see, our series of sine squared consists of two, right? One of them diverges, another converges. So the sum diverges, right? And once it is divergent, what we obtain? By comparison test, if smallest series diverges, then largest diverges as well, right? So those two implies our series of modulus diverges, and it means what? No absolute convergence, but it means that we have which convergence? Conditional, right? So conditional convergence. Right? So you see, to insert this word, we need to write down those considerations, right? That is how we prove conditional convergence of this series. Okay, so with alpha greater than 0, of course here, I'm sorry, conditionally converges x not equals 2 pi m. M natural, right? M integer. Because for x equals 2 pi m, we have zeros, and it means we have absolute convergence as well. So the last step, what to do with alpha less or equal to 0? Of course, x is not equal to 2 pi m, m integer, otherwise you have absolutely convergent series, which consists of zeros only. And so claim if alpha less or equal to 0, then the series diverges. Here we work with Cauchy criterion. So let me recall this. That is what I want to prove, right? So divergence is equivalent if we apply Cauchy criterion, negation better to say. There exists epsilon greater than 0 such that for all natural n, there exists n greater than n, and there exists p natural such that the sum k from n plus 1 up to n plus p sine kx over k power alpha is greater or equal than epsilon. That is what we want to prove. Okay. How to prove it? In fact, here we can refer, oh, maybe I was wrong, indeed. Yeah, I can refer here to necessary condition. Oh, I'm sorry. Cauchy criterion is too much here. For improper integrals, we had to use Cauchy criterion because we have no necessary condition for improper integrals. You remember I gave you, maybe I didn't give an example, but I mentioned that there is no necessary condition for improper integrals, right? And here we have necessary condition. Very good. So I don't need to go so deeply. I'm sorry. So we'll use negation of necessary condition. Necessary condition for convergence is that the limit as n goes to infinity, sine nx over n power alpha equals to 0. Since limit as n goes to infinity 1 over n power alpha is not 0 for alpha non-negative, right? Then, when this equality may happen, so it may happen both what we deduce if limit of sine and x equals to 0, right? But that is not true. That is not true. Why? Because x is not equal to 2 pi m, right? And, okay, I think maybe I mixed. No, I didn't prove it for you, sorry. Okay, so if it would be true, then also what we could deduce okay, sine n plus 1, sine nx is 0. Oh yeah, then look, the sequence of sine nx, if it has a limit 0, right, then the limit sine n plus 1x is 0 as well, right? Because it's the same sequence, just shifted a little bit. Now, what is it? Sine n plus 1x. That is sine nx times cosine x plus cosine nx times sine x. Now look what we know. Tends to 0, right? As we suppose, right? Tends to 0. That is not 0 by supposition. So what we deduce? What we deduce? Cosine nx tends to 0 as well, right? So right? And it's impossible. Why? Because sine squared nx plus cosine squared nx equals to 1. And look, we supposed sine nx equals to 0, deduced cosine nx tends to 0, so contradiction, right? And it means that for sure limit of sine nx is not equal to 0, and if it is not 0 and the limit for alpha equals to 0 it's 1, right? And for alpha less than 0 it's infinity. So for sure this limit cannot be 0. Hence necessary condition is not satisfied and we are done. So for the rest, alpha less or equal to 0, we have divergence. So answer for this example, for such kind of examples, we need to write answer. So we have absolute convergence for alpha greater than 1 and x in R, and for x equals to 2 pi m, m integer, alpha arbitrary. All right? And for others, okay, conditional convergence. Conditional convergence we have when for alpha from 0 to 1 x not equals to 2 pi m integer, and we have divergence for alpha less or equal to 0 x not equals 2 pi m integer. That's it. That is, roughly speaking, 3 branches of solution, typical branches, when you need to study absolute and conditional convergence of series. Example 2, it will be not so complete, just to refer to others' test, how it works sometimes. So, example 2, investigate convergence of such a series and for the sake of simplicity I'll suppose alpha positive. Alpha positive. So what to do here. Here we apply Abel's test. So, first part, we have convergent series. Converges alpha positive x and r by example 1, which we considered just now, right? And second, the sequence 1 plus 1 over n power n is monotone and bounded. Okay, why it is monotone? It was proved when we considered, remember, limit 1 plus 1 over n power n equals to e, right? When we proved that the sequence 1 plus 1 over n power n has a limit, we proved it's monotone and bounded. That is what we did, in fact. And now you see, Abel test says, okay, we have convergent series and we have monotone and bounded sequence. Hence, our series converges. Hence, our series converges. Next question, how it converges. How it converges. Okay. Of course, we may estimate like that, like we did for the former example for the first part. So look. I can estimate sin nx by 1, right? And also, again, refer to boundedness of our sequence. So, less or equal c over n power alpha. And the series converges for alpha greater than 1. So it means that our series converges. Okay. We proved that for alpha greater than 0 it converges by Abel test. Now we have for alpha greater than 1 it converges absolutely. For others alpha, it converges conditionally. Why? Because, once again, we can write 1 plus 1 over n sin nx over n power alpha greater or equal than 1 plus 1 over n power n sine squared nx, and alpha equals to 1 plus 1 over n power n 1 minus cosine 2nx over n power alpha. This multiplier is not important once again, so we have convergence of the first, divergence of the first for this alpha, right? Convergence of second, and it gives divergence of our series with modulus, so conditional convergence of the series on the question. So again, same considerations as before, which I don't want to repeat. Okay, let's have a break. And I would like to give a remark. If both AN and BN are non-negative, right? And AN is equivalent to BN as n tends to infinity, then both series AN and BN converge or diverge simultaneously. And that is very useful assertion. It can be proved very easily using comparison test. In fact, it's an easy consequence of comparison test. It follows from comparison test. Why? So if limit AN over BN equals to 1, and that is equivalence, right? Then what it means? Then there exists C1, C2 positive constant such that for all n greater than some natural number, we have C1 Bn less or equal An less or equal C2 Bn. So ratio between An and Bn is separate from 0 and from infinity. It is concluded in some limits, in positive limits. Hence, if the series of Bn converges, then the series of An converges by comparison test. And if series of An converges, then Bn converges again by comparison test. And divergence analogously. That is how it is proved. Just an easy consequence. But in fact, I give this remark for the sake of very popular mistake. Look, that is valid only for non-negative. That is very important thing. It doesn't work in general for arbitrary sequences. And let me give an example. So those conditions are very important. So don't apply it. Don't apply it for conditional convergence, let's say. Because for absolute convergence, no problem. When you study absolute convergence, you put modulus, right? Then automatically you have non-negative terms, right? So you can apply this for absolute convergence as well. But for conditional convergence, it doesn't work. And let me give an example. Okay, example 3. Let it be series like that, sine n over square root of n plus sine n. Look, you can write like that. Is it true? Yes. Why? What means equivalence? You divide y by another, right? Look what it gives. Okay, what is it? 1 over 1 plus sine n over square root of n, right? And it tends to what? Sine n is bounded, 1 over square root of n tends to 0, right? So you have 0 and gives 1, right? So indeed, that is true. That is true. And this series converges conditionally by example 1, right? Because alpha is 1/2. Alpha is 1/2, x is 1. Alpha 1/2, x is 1, right? So you can say, oh, they are equivalent, hence our series also converges conditionally. No. Why no? Because look, how we can represent, and that is correct representation. Look, we can do like that. Okay, first idea is absolutely the same as was before. But then, look, we have 1 plus something what tends to 0. And we can apply one of Taylor, or better to say, Maclaurin expansions. Let me recall which expansion I use. Oh, alpha x, sorry, x squared plus. Okay, in fact, I'll stop here. X tends to 0. And I want to apply it with alpha equals to, so alpha is -1. We have 1 plus x power -1. And x is, so I want to apply it, alpha is -1, x is sine n over square root of n. We can apply it because x tends to 0, right? As n tends to infinity. So, what is it? Sine n over square root of n times 1 minus sine n over square root of n plus, okay, alpha is -1, -1 minus 2 divided by 2 gives +1, sine squared n over n plus little o of this expression. Okay, then we have several terms. I can multiply inside. And now look, for the last two, I can obtain the following estimation. I will not rewrite it. This expression less or equal, look, I can estimate sine by 1 and 1 by n power 3 over 2. Okay, let it be c, because we have two terms, one of them, let me put 2 here, two terms, each of them by 1, right? And we know the series 1 over n power 3 over 2 converges, right? Hence, the series of this expression converges as well. Okay? This series converges because of that, right? So we have convergent, convergent. But the rest diverges, right? That is how we proceed, like before. Sine squared n, 1 minus cosine 2n over 2. Once again, we have 1 over 2n, the series diverges, and cosine 2n over 2n converges. So, diverges. The series of this. Those words, convergent, divergent, and convergent, refer to series with those terms, right? Series. So what we obtain? Our series diverges. So you see, this example shows that equivalences, equivalent between two sequences, doesn't help when you want to study conditional convergence. Okay, now. Okay? Yeah. Now we can move further off. And yeah, examples are over. And we move to rearrangements. And in fact, that is an explanation of the word conditional in some sense. So, theorem. Theorem 1 in this section, of course. Suppose the series converges absolutely and B1, B2, and so on is a rearrangement of A1, A2, so on. Of course, it's a little bit strange to consider rearrangement of infinite sequence, right? But nevertheless, why not? Somehow we rearrange. Then the series is absolutely convergent and its sum is equal to the sum of the original series. So, in some sense, this theorem is a generalization of commutativity law for usual sum, right? Because if you change the order of summands, then the result doesn't change. And same is true for infinite sums, but for absolute convergent series. And that is crucial, in fact. Okay, but first of all, let us prove it. So, proof. The series of modulus converges, hence the sequence of partial sums up to n is bounded. We had a theorem for non-negative terms. If we have a series of non-negative terms, then it converges if and only if the sequence of partial sums is bounded. There was such an assertion. So the sequence is bounded. Now, okay, let it be. So there exists C such that for row n natural we have sum k from 1 up to n modulo k less or equal C. That is boundedness, right? So we have boundedness of our partial sums. Now, consider partial sums of our new series of modulus once again. Okay, let it be capital M B n. We know that all those Bn are nothing else but, since that is a rearrangement, right? So it means that these are A with some numbers up to capital M, A, let's say M, right? So Bn are A with some numbers. I don't know numbers, so that Mn is a sequence of naturals. In fact, it indicates how we rearrange, right? So Mn is rearrangement of naturals. We rearrange all naturals. This rearrange of naturals gives us rearrangement of our sequence An, which gives Bn. Okay, now that is less or equal than sum k from 1 up to maximum of M1 so on up to M with capital M, right? So what I do? I look at all indices which we meet, right? And then what I do? I consider partial sum of all modulus AK, right? Starting from 1 up to this maximal index which we met, right? That is what is written. That is obvious, right? Because I added some non-negative terms. Modulus are non-negative. I add them. And you see, we know that arbitrary partial sum of modulo AK is bounded by this C. So it is less or equal than C. And what it means? We considered arbitrary partial sum of our B, right? Modulo B. And it is bounded. Hence, because of non-negativity of modulus, the series of modulo Bn converges. So if partial sums are bounded of a series of non-negative terms, then the series converges. So it gives absolute convergence of the series of Bn. What remains? We need to prove that we have equality between sums of those two series. So now consider partial sums. Okay, let me denote them like Sn are partial sums of the original series, and Sm star are partial sum of rearranged series B. So with star means that it is after rearrangement. Okay. We know there exist limits s equals to limit as n tends to infinity Sn, s star equals to limit as m tends to infinity Sm star. Why? Because we know the series of Bn is absolutely convergent, and if it is absolutely convergent, then it is convergent. So the question is to prove that those S and S star are equal, right? Okay. Let me estimate difference between Sn and Sm star. Okay. Look, I want to take n, let it be n is greater than maximum of OK such that AK equals to B J 1 up to n. Maybe not very good writing, because you see, rearrangement means that we change numbers. We don't exclude the case when we have equal terms. It's not important. But nevertheless, we rearrange, because just numbers of indices are important. Indices are important for us. And you see, so we know that, so what I want to consider, Sm star consists of some bk's, right? Or bj's, right? Bj's. And all those bj's are A with some numbers, right? And I want to include all of them into Sn. That's it. So all indices of A such that they are bj's are included into Sn, right? Then what is it? So every bj from this Sm star is somewhere here, right? So what remains? What remains are some others. So it is less or equal than the sum of k from m plus 1 up to infinity bk. And that is a remainder of convergent series. So it tends to 0 as m tends to infinity. So what we obtain? For sufficiently large n, the difference between Sn and Sm star tends to 0 as m goes to infinity. And it means that in fact, you see, what happens? So it tends to 0, so what I can do, okay. Sorry, it's better to do like that. It's not good, sorry. Look, this is valid, right? So we deduce from this inequality. So if we have something, we have an equality which is valid for all n greater than this maximum, right? For a moment, fix m. M is fixed, okay? Since it is valid for arbitrary n greater than this maximum, I can tend n to infinity. So n tends to infinity. M is fixed. Sn tends to what? Sn tends to S, right? So we obtain S minus Sm star is less or equal to the same number as we had. Right? Now, as m tends to infinity, the right-hand side tends to 0, right? Hence, the left-hand side tends to 0 as well. And it gives us what? S star equals to S. Right? So, this tends to 0. Hence, S star equals to S as we wanted. And then theorem is proved. Okay. And let me formulate without proof theorem 2. Riemann theorem on rearrangements of conditional series. If the series is conditionally convergent, okay, I should change the title, I guess. Okay, then for all L from R, or L equals to minus infinity, or L equals to infinity, there exists a rearrangement B1, B2, B3, so on, of A1, A2, A3, so on, such that limit as n goes to infinity of partial sums equals to n. That is without proof. Proof is sufficiently long, but it is completely wonderful. Look what it says. And that explains the word conditionally, in fact. Why? Because, as you know, if you have finitely many terms in a sum, right, then doesn't matter how you rearrange it, right? The result will be the same. But for infinitely many terms, the situation is completely different. That is why it is conditionally convergent. Because the order is very important now, right? And you see how it is important. You can rearrange terms in your infinite sum in such a way that the result will be completely arbitrary. It can be infinite plus, infinite minus. It can be arbitrary finite number, absolutely arbitrary, right? So, for absolutely convergent series, you have complete analog between finite sum and infinite sum. But for conditional convergent infinite series, nothing, right? So you see the order is very important. You cannot change order of terms in infinite series in general. You can do it only for absolutely convergent series. Okay, now about products. Oops. Absolute convergence here was very important for this. The question is why absolute convergence was important. Because we referred to boundedness of those partial sums. And in fact, the proof of Riemann theorems just uses this idea. So how it works? Okay, I have 5 minutes instead of products. I'll explain how it works. Sketch of the proof. Because of this question, you see, so how it works? Conditionally convergent. So we know that the series of modulus is divergent. And now what we do? We consider the following numbers. An plus is equal to, let's say, maximum of an and 0. And an minus is analogously maximum of minus an 0. These are positive and negative parts. So with those notations, these are notations, we have modulo an plus an minus, and an is an plus minus an minus. So it is easy to prove that from conditional convergence it follows that both series of an plus and an minus diverge, each of them. So you see, the series of modulus is divergent. It means that if we add each time modulus, so we increase, right? Then it goes to infinity. But if you consider the series itself, that is not the case. What it means? It means that somehow we add positive, then subtract, right? Add negative, then again positive, again negative, and so on. And then somehow they cancel each other in such a way that we obtain as a result finite sum, right? Now how the proof of Riemann theorem works. Look, we have divergent. It means that if we look only at positive terms, right? Then what happens? We add positive terms and they grow arbitrarily large, right? And what do we want? Okay, it grows. The first time when it overcomes L, will stop. So look, we add those positive until the first moment when we will be greater than capital L. So just one term smaller, we are less. Partial sum is less than capital L. And then it becomes greater, right? So the first term when we overcome L. So it looks like, look, so I choose L, right? We add positive terms until the moment when partial sum first time it will be greater than capital L, right? Now we start to take negative. From the very first, we take negative. We know it is also infinitely large, right? So it means that we can add negative up to the moment when we will be to the left of capital L, right? Once we achieved it, we stop again. Go back to our positive, and we take the rest, take once again positive terms from the rest of this series up to the moment when we will be greater than capital L, right? And repeat it to the right, to the left, to the right, to the left, and so on. And that is the way how Riemann theorem is proved. Okay, technically it is not so easy, of course, but I tried to explain you the idea, right? And that is, you see, it doesn't matter where you choose capital L. Because of divergence of those series, both consist of non-negative terms, and it means that we may find a partial sum which will be greater than arbitrary given number L. That is how it works. Okay, so I didn't start. Yeah, very famous series which is conditionally convergent is that one. That is conditionally convergent term, conditionally convergent series, and it's very popular because you can construct directly, not so difficult, you can find it in literature. So the sum of this series is equal to logarithm 2, in fact, but you can rearrange it to obtain a different value. That is very practically you should proceed in analogous way to the proof of Riemann theorem, of course, but it can be done in concrete way. So if you want to understand better how the proof of Riemann theorem works, you can look at examples which can be found even in textbook on calculus, not only on analysis. Okay, that's all for today. Thanks for your attention.